All right. So to get started today, it is Friday the 20th. For today's assignment, what I'm going to do is I'm going to record myself talking through our Chapter 5, Section 2 guided notes. Now, I have 15 minutes to be able to do this. I think I'll be able to do it. If I need to make 2 recordings, I will. But I wanted to get started here and say that the best way that you guys should be listening to this audio is with your guided notes in some form or another next to you, and also your textbook next to you. So if you didn't bring your textbook home, you guys know that you have the digital copy, you have the PDF available to you. Again, it is on Google Classroom. It is hyperlinked textbook under your classwork page, I believe. So if you can pull up your PDF textbook, it might take a minute to load. I would get that ready. In your stream, I'll be posting the guided notes. I think that you guys might be able to know how to make a copy and type directly into the guided notes if you would like to have a digital copy. If not, there could be the option if you are able to print these at home. I think that it would be a really great opportunity to actually print them, actually write in the guided notes. That being said, I don't have a printer at my apartment, so if you don't have a printer, that's okay. What I did instead is I just briefly rewrote them. So you don't have to rewrite every single thing. I will also be making this assignment, today's assignment, as well as Monday's assignment. So if it's something that you want to put in 15 minutes of work today and 15 minutes of work on Monday, it might not seem like too much, but I know it is, it's just one more thing not having the guided notes printed in front of you. All right, so I'm going to get started here. Again, you can always pause my audio and be able to open up all of the images or the documents that you need or gather your materials to take notes. Started here, just to go over our vocab and our objectives first. We've got 4 vocab terms: salt, something you've heard of before, lattice energy, crystal lattice, and unit cell. Your objectives for this section: 1, be able to describe the process of forming an ionic bond. 2, explain how the properties of ionic compounds depend on the nature of ionic bonds. And 3, describe the structure of salt crystals. So again, same objectives, same vocab terms on your textbook. Also, a heads up, if you're looking for the page numbers, this is page 166 in your physical textbook, or this is 184 in your PDF of your textbook. All right, getting started with these blanks here. The first kind of header that we're looking at in our guided notes says ionic bonds form together between ions of opposite charges. So we have talked about these 2 different flavors of ions. They are cations and anions. In fact, knowing what you know about cations being positively cute and anions sounding like onions, that's, onions, when you cut them, they make you cry. It's a negative emotion. You might be able to fill these blanks in. Let's take a look. First blank. The force of attraction between a blank charged cation and a blank charged anion is what is called a blank. So we are looking at this first one. We're talking about what is the charge of a cation. Our first blank must be positive. So the force of attraction between a positively charged cation. And then it's a next one, a negatively charged anion. So again, first 2 blanks, positively charged, negatively charged. I like to put a little plus with a circle around it, a little minus with a circle around it, just for some visual cues. And that forms what we will call an ionic bond. An ionic bond. Moving right along here, cations form from, well, anions form from. So this is always going to happen. This is going to be a set trend. Cations are always going to form from metals, versus our anions are always going to form from nonmetals. So this is based on our ionization energy trend, also some predictive properties of cations and anions based on their number of valence electrons. Let's take our metals, for example. So cations will form from metals. We know this to be true because something like an alkali metal would form a +1 charge in that it has 1 valence electron. It's really predictable. It's always going to do that one thing where it loses 1 electron. If you lose the negative particle from your life, you lose the electron, you're becoming positive. So cations will always form from metals, while anions will always form from nonmetals. So our classic example of chlorine, we can say, well, chlorine is a halogen. That's a type of nonmetal. It's right next to those other noble gases. It's just the noble gases don't react. So with our halogens or any other nonmetal, they're closer to having an octet in that they will have something like 5, 6, 7 valence electrons. So it's always going to be easier for them to gain electrons. So if you're gaining electrons, you're gaining negative particles, you are becoming negative. So we know that cations will always form from metals, anions will always form from nonmetals. So another way that we could call an ionic bond, we could also say an ionic bond is a bond between a metal and a nonmetal. That is definitely going to be one of the ways that I refer to it in class, in practice problems, and that's a really easy way to know, do I have an ionic bond? So if we know an ionic bond is also a bond between a metal and a nonmetal, I might say something to you guys like, what type of bond is between lithium and oxygen? And you would look on the periodic table and say, oh, lithium, that's a metal, that's an alkali metal. It's on the left of the periodic table. Oxygen, that's a nonmetal, it's on the right-hand side of the periodic table. And again, there's a separatory staircase. You guys have it on your periodic tables. It might be really small, a thin black line if you hadn't created it on your color-coded periodic tables, those study guides we made. But we know that if you do have any combination of a metal and a nonmetal, you could say, oh, that's an ionic bond. So that is definitely one way that I'm going to be referring to it as we go forward. Next, salt is not just table salt then, like NaCl, but also salt is also any one of thousands of different ionic compounds. So this blank in your notes, salt is not just table salt like NaCl, sodium chloride, but also any one of thousands of different ionic compounds. Any one of thousands of different ionic compounds. So what we're saying is any combination of a metal and a nonmetal is a salt. So table salt, sodium chloride, is like the common salt. When people say, oh, pass me the salt, that's what they're talking about. But we don't have too much snow outside, but the salt that you're putting out perhaps on your driveway when it's icy, that is also a different type of salt. You just might not want to eat it. So although most salts, ionic compounds, do have like a tasty, salty taste to them, sodium chloride is the one that is not really hazardous to eat. There's a lot of other salts out there that, although we will call them salts, they might contain, and I'm not saying that the stuff we put on our driveway is, but there are a lot of salts out there that are really hazardous. So going forwards, after these guided notes, so maybe next week, we're going to do something where I'll have you guys make like a mini poster. You can get a little creative. I'll have you guys doing it for a bunch of days, but I'll have you randomize a random salt. So I'm not sure how I'm going to do it. I usually have kids pick one cation and one anion out of a bag. I think maybe this time I might, I don't know, I might give it to you and just give you one, or maybe I'll use some online randomizer or something like that. But what we would say is, even though you have a random metal and a random nonmetal, it would be a salt. It would be an ionic compound. So what we're going to describe kind of in the rest of these guided notes is it doesn't matter what the metal and the nonmetal are. And again, there's some really crazy ones out there, but it's going to be very similar to every other ionic compound, every other salt out there. So that's also why sodium chloride is a lovely example. We have a few more examples down here. You have some like bolded arrows. You see NaCl, NaBr, CSCI, or no, pardon me, CSCl. I should say that too. If it's ever carbon and iodine, just assume it's chlorine. The capital C, lowercase l for chlorine. I even mistakenly, I just read it as carbon iodine. So just a little heads up. But what we are looking at is we would recognize that all of these examples have a metal, like sodium is a metal, or cesium is a metal, or calcium is a metal. And they also have a non-metal, like chlorine, bromine, oxygen. There are a couple other blanks in here, so if you guys want to make any other metal-non-metal combination, you certainly can. I have a few in here. This is usually when I have you turn and talk in class. So another one that could be an example to put down, magnesium oxide. You could write it out, magnesium oxide, or you could write the formula. It's capital M, lowercase g, capital O. And another example is magnesium chloride. You actually have it right down here as this second example, MgCl2. So what I would want to say with all of these examples is also our next blank, that salts are electrically neutral. So the next blank here, salts are electrically neutral. So we say salts are electrically neutral, meaning their overall charge is going to be net zero. So although a metal might be a cation and it has like a +1 charge, or our anion might be a -1 charge, when they come together, they're always going to come together on the number line. So you have equal but opposite cations and anions. So we see this in our first example of sodium chloride. So here we have an equation where sodium Na plus is forming with Cl minus. On my page, I have color-coded plus and minuses. I think that's just a formatting error. I don't mean to show anything with like a yellow plus sign or a blue minus sign. Typically, these are black and white when I hand them out. But what we're looking at here is we have Na plus and Cl minus. So there's an invisible one on both of these, kind of like in math class where you have one X. It's just written as X. So if you have sodium +1 and chlorine -1, that's why your overall ionic compound is just written as NaCl, because the +1 of your cation, the -1 of your anion, they come together to be 0 on your number line. So what we're doing here is we're adding them together. +1 plus a -1 is just going to be 0. And that's our neutral charge. That's what we need for every salt that forms. So over here in our second example, we have Mg2 plus 2Cl1 minus. So what we're looking at in this equation, we have magnesium and we have chlorine. Now the interesting thing here is, although we can form a ionic compound between any metal and a nonmetal, because it has to be neutral, if we were forming it between something like magnesium and chlorine, which don't have the exact same equal but opposite charge, we have to kind of reach into a bag and say, how many do I need of each of these? So with magnesium, we have a +2 charge. It has 2 valence electrons, remember, so it's going to lose both. Chlorine has a -1 charge. Again, has 7 valence electrons. It's going to gain 1. So these set predictable charges of a 2 plus and a -1, they're kind of, we could say least common multiple is 2. So we have to get to +2 and -2. +2 for our cation side, -2 for our anion side. So you'll notice I have the invisible coefficient of 1 on this magnesium, because if I just have one atom of magnesium, that's +2. But with chlorine, because it's -1, well, I'm going to need 2 atoms of chlorine. If I have 2 atoms of chlorine, that means overall I have a -2 for my anion side of my ionic compound. And then we can just smush them together. If we have a -2 and a +2, that'll be neutral overall. So that's why in our ionic compound, the formula is MgCl2, where we only need 1 atom of magnesium, but we do need 2 atoms of chlorine to make it neutral. So you guys are going to be doing this yourself when we do that little mini poster project. I'm going to be calling it the Get Salty poster. All right, we got a few more blanks here on the bottom of our first page, and then we'll move on to the next page. Transferring electrons involves energy changes. So removing or gaining electrons require energy changes. Just like when we looked at our ionization energy, we said that the ionization energy trend, well, ionization energy is how much energy is required to remove an electron. So we see that again here. Removing an electron, aka creating a cation, remember to remind yourself, if you want to draw a plus sign, you can, but creating a cation, and that requires energy. Our second bullet point here, gaining an electron or creating an anion releases energy. So again, if you're removing an electron, it requires energy to rip it away. But if you're gaining an electron, it's going to be releasing energy. So this whole idea of gaining and losing energy, this is just doubling down on the thought that we have a law of conservation of energy We have a law of conservation of mass. We understand electrons to, although they are particle waves, have some very, very tiny mass. So this whole thing is saying that we are having chemical